Hello, good afternoon. I'm going to be talking today about Rapids and Emo Curator. Both of these are like software frameworks focused on accelerating data processing and data science. Uh, they're both open source, so I won't go too deep into technical details in this presentation, more covering the features that they have. But if you're curious about diving deeper, feel free to check out the code on GitHub and see the inner workings for yourself, as well as trying it out on your own data. So the demands for data and compute in data science are growing at an incredible pace. Moore's law meant that CPU's processing capacity was growing 2x every year up until now. It's been plateauing. So the paradigm of parallel computation has become quite critical in keeping the rate of processing continuing to grow at that pace year on year. And the main difference between a CPU and a GPU really is CPU does everything serially, whereas GPU can do things in parallel. This has become quite relevant in today's time because of AI, since it does a lot of matrix multiplication, which is very conducive to parallelization. But this parallelization can help accelerate a bunch of different other workloads that are not just AI. So things like data processing, traditional linear regressions, etc., etc. So what does Rapids cover? We have sort of three main focuses. The data loading part, so here you have Rapids cuDF, which is a sort of pandas plug-and-play replacement. Apache Spark, so a lot of like today's data processing is done in Spark, so we simply accelerate that on GPUs. Dask. Then when it comes to model training, graph analytics, so your traditional like page rank, community detections on graphs can be extremely accelerated with GPUs. cuML, so think of your like sklearn type libraries with all those traditional machine learning algorithms can be accelerated. Deep learning, we already know can be accelerated, but we really focused on graph neural networks. So sort of a next step on more traditional graph analytics. And finally, when it comes to model inference, both on vector search and also for deploying inference of things like tree models. So if you're deploying XGBoost, we have a forest inference library dedicated to accelerating that inference. There's a big hierarchy of like toolkits that are relevant, and today we're really going to be focusing on the top layer where everything is sort of plug and play, no code change required to get your data processes accelerated. Here's a few examples of clients we have worked with to accelerate their data workloads with GPUs. AstraZeneca, for example, uses cuGraph as a part of their internal knowledge graph of biological entities. So you can do page rank type algorithms up to 100 times faster, which does accelerate drug discovery process. Similarly, with Walmart, we've done some work with accelerating forecasting of like logistics, etc. Yeah, a lot of people use this. Let's start covering like the most basic acceleration that's available is with pandas. Pandas is like in the toolkit of most data scientists. And so we wanted to start off with accelerating that. If you want to have a GPU accelerated pandas version, you simply have to add one extra line on top of that. Obviously, you also have a GPU underneath. And this sort of hijacks the import process in Python to any operation that can be accelerated with GPU will be passed on, and any other operation will just run in CPU as normal. So here you have the same code executed with CPU and GPU. Again, single line difference. And you could see that this is a very simple map and then grouped by on New York City's parking violations, which there are a lot of them. And you can see running on CPU on multiple cores, it takes almost 50 seconds, whereas on GPU, this takes 600 milliseconds. So almost 100x speed up. And this is because when you're doing a map, on CPU, you're doing it sequentially, but operations like map can be parallelized very easily because there is no sequential dependency in that operation. And so any sort of data frame operation you could think that's not sequential in nature will probably really benefit from GPU acceleration. Similarly, with Spark, you can do a one-line change and get huge acceleration benefits. So with this 3 terabyte data set, you can see it's almost 6 times faster. And oftentimes people are like, oh yeah, 6 times faster, but GPUs are much more expensive than CPUs. Will this save me any money? And you can see that it's almost an 80% cost saving, for example, on AWS, from going from a CPU-based instance, an R6 ID, to a G5. You can get the 6x speed up, which not only saves developer time, but also saves costs. Similarly, we have support for Dask. Now, diving into the machine learning part, the more traditional algorithms, so random forests, linear regressions, clustering, etc. We can provide huge accelerations. A lot of these more traditional regression models in very big data environments are slowly being phased out in exchange for like transformer type models. However, things like clustering will always be relevant because that's critical to like doing data science experimental design. So if you're going to actually accelerate your PCA clustering, your k-means clustering, TSNE, whatever, that's a huge boost in developer productivity. And again, single line code change. All your sklearn code will run in GPU accelerated fashion. XGBoost already by default supports CUDA acceleration. This is like a favorite for any type of forecasting. Most like fraud workloads will run on top of XGBoost type classifier. And yeah, if you have really big amounts of data, you can see up to 20x speedups when switching over to GPU. Similarly for the machine learning capabilities of Spark. So any sort of Spark machine learning that you're doing can be extremely accelerated with GPUs. Finally, our cuGraph, so our graph analytics framework, is like one of the things we've seen gain the most adoption, especially when it comes to life sciences. Can really make sort of workloads that weren't possible up until now possible by allowing for much more costed refreshes of your data. So instead of taking 2 weeks to recalculate your graph, you can now do it in a couple of days. And this means you can get quite refreshed analytics. So now I'll be diving into the applications of this sort of accelerated data processing in the realm of generative AI. And this is the library we're seeing like have the most uptake, the biggest uptake in adoption. Again, it's open source, so feel free to check it out and gain further details into it. We have a big sort of set of libraries dedicated to generative AI. From Curator is the one we'll be focusing on. If you're curious, we have Nemo Customizer, which focuses on things like model fine-tuning, so LoRa or reinforcement learning, etc. evaluator, so microservices that you can integrate into your CI/CD pipelines to keep track of how your models are doing A/B type tests, etc. Retriever, really focused on RAG type workflows. Guardrails for more customer-facing things, and NVIDIA NIM, which is our inference microservice. So if you've used VLLM or SGLang or anything like that, it's our own offering for that, but made to run as fast as possible in our hardware. And so you can get quite good throughput and latency boosts from switching over to that. But that won't be the focus today. I'll be focusing on mainly text processing and video processing, because image processing is quite similar to, will end up being similar to video processing. So I thought I'd spare you like very similar slides from one to the other. But looking at the text processing part, there are three main key components that can be accelerated. When it comes to synthetic data generation, so that might be from adding metadata, using LLMs to add metadata to your documents for easier retrieval, or adding summaries to documents, or rephrasing them into different languages to make your downstream models better at multilingual capabilities. Quality filtering and deduplication are huge. So, for example, if you work with financial news data sets, and you're trying to label these and use these downstream to train your model, a lot of financial news are semantically the same. So if you keep like JP Morgan sets price target for this company to $80, and then you have another title that sets price target to $120, this is semantically the same. So you don't want to have loads of semantic duplicates in your training data, because that will mean that your downstream models will overfit. So you want to, good data leads to good models. And if you're fine-tuning LLMs, you really want to focus on strong deduplication. And also, when it comes to quality filtering, removing poor data quality. So like things that might have personal identification, text formatting issues. It's maybe a scanned PDF and it's all broken. You don't want that to be passed down to your model, or toxic or harmful content. These things apply also to image processing and video processing, just at different scales. A lot of what's available in the open source currently does not leverage GPUs, and especially when it comes to like terabytes of data, and I'll give you an example later on, this can really hinder developer productivity. So we built Nemo Curator to provide you like a sort of out-of-the-box tool set that can help with these sort of steps. So let's look at the text processing, a typical like data processing architecture, and where Nemo Curator and NIMs can come in. So your typical cleaning and pre-processing will be done on Spark or Hadoop or any other framework, and we've already covered how those can be accelerated. Then you probably want to start by doing some sort of quality filtering. Maybe the simplest thing we can focus on is removing any documents that might have personal identification. So there you can use, we have dedicated NIMs. So again, these are just containers with models inside, focused on filtering for these type of heuristics. Secondly, you'll have deduplication. So the simplest type would be exact deduplication. So you hash all your documents, see if there are any hash collisions. Doing this on CPU is extremely slow, and this really benefits from parallelization. So again, 200x type acceleration on that. But then when it comes to semantic things, so like the cat chased the ball or the dog chased the ball are very semantically similar data points that you might want to filter one of those out. There we have models specific to this. Essentially, you'll be embedding all of these into a vector space, and if any of these elements have a sufficient overlap in vector space with what you're filtering against, they'll be removed. And again, this really benefits from GPU acceleration. Finally, when it comes to more sophisticated quality filtering, we provide a set of reward models as well as other types of embedding models that are not just focused on deduplication, but on, for example, toxic content removal, if you're training your model on data from 4chan or something. Which, again, can be hugely accelerated. I'll skip this part and get to this slide. So maybe you're familiar with the Red Pajama dataset, or maybe you've heard of like Fine Web. So these are datasets that are like web crawl. For example, Fine Web was published by Hugging Face, and it's just a set of like really high quality web pages. And these are all in the order of like terabytes, and they have trillions of tokens. But you still, if you're using these downstream to maybe do continued pre-training on your models, you want to be processing this data with all of the key points are raised before, just have into consideration. And as you can see, with simple free H100s versus hundreds of CPUs, we can see a 16 times faster processing time. And this can lead up to 40% savings. Obviously, it will be dependent on your cloud service provider, or if you're hosting this on-prem, it'll probably be even higher. And you can see that as you increase the number of nodes, the sort of speed up is almost linear. Although this is a little bit contingent on the type of networking you have. I'll jump over this slide, but it's just essentially a few of our clients that have used the NeMo Curator framework to accelerate their sort of data processing needs. And I thought the VTEL solutions one was quite interesting. One of the projects we worked on, they wanted to do continued pre-training on one of the like more popular open source models to make it better at Vietnamese. And so they essentially needed to filter a bunch of web data and documents that they had to only contain Vietnamese language. And you'd think this would be easy, but there's a lot of data, so the speed up really came in handy and reduced a lot, provided a lot of cost savings. Again, it's a very similar pipeline when it comes to video. This is becoming quite relevant for like robotics companies, self-driving companies, and like image model providers, like Stable Diffusion, etc. Where you, again, want to do this sort of semantic deduplication on your data set, only keep high quality examples so that your models can learn best. And I don't feel like it's really worth covering the other steps because they'll be very similar. But the annotation step here is unique to video. And this essentially uses our model Cosmos. So if you want to have paired video with the annotation, or similarly for images, if you want to train an image generation model, you need to have pairs of images and text. And so we've trained this Cosmos model on many, many millions of hours of videos, and you can then leverage it for your own internal data sets to label both images and videos. And yeah, it's, again, very similar type workload, but at a different scale. When it comes to videos, we're talking petabytes. And so I think here people are not really considering not using GPUs for that, but what we've tried to do is, through the work we've done with various companies, to create an open source library that covers some of the main data processing steps that you would have for video processing. And yeah. I mean, yeah, for videos, the CPU comparison is not really fair because, yeah, the speed up is going to be huge. But I do really encourage you to try this out if it's relevant. And also our visual language model, the Cosmos model, is really optimized for throughput and latency. So versus like open source models that are available on Hugging Face, you can see up to an 11x higher throughput. And again, some of the customers we've worked with to use our libraries and test them out and help us improve it. And that's it. I think I have a couple minutes, so if there's any interest in Q&A, that would be the chance. I think that we need a microphone, otherwise other people.
Hi, thank you. My question is like to use the NVIDIA Rapids. Basically, you are using GPU underneath, isn't it? So, in an organization which already has a platform decided, like maybe some cloud like AWS probably or Azure or one of the main ones, and to be able to do this, do they have to go to another platform, or within that same cloud can they have GPU enabled virtual machines or something like that?
Yeah, exactly. So I'll go back here to the AWS example. So here, this is on AWS. So this was a Spark job that would be running on these R6 ID machines. And the only change that you need to do to leverage is adding that code line change, but also the type of machine that you're hosting on. So it can be either on demand or if you have reservations ahead. It's just a matter of changing what type of EC2 instance you're using. And this is the same for GCP, Azure. Again, it's just change the machine and change the line of code so that it can leverage the GPU.
So this can be done for specific workloads which need higher resource requirements, probably.
Yeah, so this will work for any sort of workload that benefits from parallelization. So any sort of tables that have high cardinality, and if you're doing maps, etc., will really be accelerated.
Just one more question, please. So this Spark accelerator, for example, Spark already does parallel processing, right? But is it like, so if you, when it is already distributed the workload into smaller chunks in multiple processors, is it that within the processor you're trying to further parallelize using GPUs?
Yes, yes, correct.
Hi, yeah, so, on Databricks, you've got the virtual machines to run your jobs and everything like that. Will they have NVIDIA powering chips to do that? So will we be able to use this technology in Databricks?
Yeah, I believe it does. As long as you have the GPUs, it'll work there. Our integration with Databricks is maybe the less mature one out of versus CSPs like AWS, GCP, etc. But it is possible to do it. It's just maybe it'll be less streamlined. You need to play a little bit more around with your configs and stuff.
Thank you. So with this, you could have, say, you could have a containerized, let's say, containerized sort of that like a feature creation job, for example, and then run it, say, I'm picturing a scenario where you could say the very same container on AWS, it would run, if there is a GPU, it will do that. And then if there isn't, it will just continue as normal instead of having to have two separately managed.
Yeah, exactly. So this diagram here sort of applies not just to the pandas library, but to Spark, etc. Anything, if you can have the same code, anything that will not be able to run on GPU will just run on CPU. So you don't need to be thinking like this. Yeah, it should streamlined work on everything. I don't think there's any other question. Yeah, we could do one more.
So NVIDIA is getting into the data centers business, isn't it? So are you planning to have your own cloud as well, just like AWS, Azure?
No. Those are our partners, so we don't want to compete on that. There are new clouds like CoreWeave, sort of specializing on GPU type compute that we are investors in, but no plan to do our own sort of cloud service
Sorry,
provider.
could you say that name again? I couldn't get it.
CoreWeave.
Thank you.
Think if there's no other questions, maybe we can finish it. Thank you.